So we'll talk mainly about my package called bigstatsr, and then in the end I will quickly talk about 2 other packages. But yeah, focusing mostly on this one because it's the most broadly, like you can use it for many different data as long as it's matrix format, so it can be used by many people. So some motivation behind this work. So why did I implement this package? So I'm working in human genetics. We have very large data. So it's genotype data, so matrices that store the allele counts for each individual that you have that are stored in rows, and all the genetic position as columns. So you can have many genetic positions, so many variables, so hundreds of thousands. And now with imputed data, you can have like up to tens of millions of variables, so many variables. And actually, we also have many individuals. So previous data set that I used, I had like 15,000 individuals. It was already a large data set, like, I don't know, 5 years ago. But now it's kind of a small data set, and now we have like things like the UK Biobank where we have like 500,000 individuals. So you can have matrices of 500,000 individuals, so the number of rows times like millions of genetic variants, the variables. So it's like very large data. But I want to use R because I'm familiar with R. I know many things. I know to do many things with R, use many packages that are very useful. So I don't want to leave R. I want to do everything in R. So I want to analyze this large data in R. So the solution I found for that, for example, if you have a R matrix that is 100 gigabytes and have a computer with only 64 gigabytes of RAM, then you can't really have that in memory. So what you can do is store this data on disk. So you have a binary file on disk, and you access it using memory mapping. So I provide in my package, I provide a format called FBM for a file byte big matrix, which is very similar to the format used in the package big memory, which has been there for like quite some time now. Yeah, there are a few differences if you want to look at them. Look at this vignette. I will share the link of this presentation at the end. So just quickly explain to you what memory mapping, how it works. So for example, you have your big matrix, okay? You want to access the first element, which is the first row and first column. So when you access some data, you access it by block. So you access a block of memory. So basically, let's say we access the first column. So it's accessed in memory from this to memory. Then we access the second element. So usually the matrices are stored column by column. So the second element would be the second row and first column. So basically it's already in memory because when you access the first element, you access the first column, the whole first column. It's already in memory, so it's very fast. So you access all the elements of the first column, it's very fast. Then you access the second column. So you access one from disk and then all the other elements from memory. And you can access many columns like that until you have enough memory for that. At some point, you don't have enough memory anymore to access new columns. And basically some space is freed automatically for you so that other columns can be accessed into memory. And what is nice with memory mapping is that everything here is managed by the operating system. So everything is seamless. You don't have to do it, free some memory and then load some new columns. Everything is done for you, so you don't have to think about it. So With this format, that provides some simple accessors. So just a quick example. So if I make this FBM with 2 rows and 5 columns, and then I initialize to 1 to 10 values, I specify a backing file which would be where the data is stored on disk. So actually, you can see this test.pk. It's the binary file that actually stores the data on disk. Then I can, as a standard R matrix, I can just use the standard accessor with the square brackets to access, for example, the first column, the first row. So again, the data is stored, column by column. And I said, like, for example, if you access the first element of the first column, you access the whole column basically, because you access data from like in blocks. So actually, when you access the first row, you will access the first column, the second column, you will access the whole data. So try not to access a subset of rows, try to access a subset of columns to work with blocks of columns instead of with blocks of rows. You could access the whole data as a standard R matrix using the 2 square brackets without anything inside. But yeah, don't do that because you're supposed to have very large data, so it's not supposed to fit in memory. So if you want, for example, to compute the call sums of the whole data, so you could, access as a standard matrix and then use the standard R function call sums. But yeah, you don't want to do that. So a simple strategy to apply an R function to this large data is to use the split apply combine strategy. So if you can, access only the first 1000 columns, apply the function you're interested in. So here call sums. So you get the call sums for the first 1000 columns. And then you do it for the second block of columns, and so on. And then you can just concatenate all the results together to get the results you want for all the variables. And so this split apply combine strategy is implemented in the package, in the function big_apply for convenience for you. And actually, you can run this in parallel, so you can, access the blocks and apply the function in parallel to make it faster. It's just an argument in the function. So we've seen how to access it in the data in R, but we also maybe want to access the data within C++ or RCPP if we want to code some very efficient algorithm in C++. So to do that, it's very easy because I provide some accessor here that is behaving similarly as a standard R matrix. So the standard R matrix in RCPP is called a numeric matrix. And with a numeric matrix, you have the methods like nrow and ncol to get the number of rows and columns. And then you have the accessor with the parentheses to access element I and j, like row I and column j. It's exactly the same with this format and this accessor. So by just adding these 2 lines at the beginning of your code, you can actually use the same code as you would use with a standard RCPP matrix. So it's easy to do. Okay, I will now present some examples from my work, some motivations. See like some of the functions that are implemented and why they are useful and fast they are. So in my work, we are interested in computing the first principal components of a very large matrix, so the genotype matrix. So here I'm talking about partial singular value decomposition, so it's the same as computing the first species, the principal components. And for a matrix of 15,000 individuals and 100,000 variables, if I want to compute the 10 first species, using 6 scores, it's only 1 minute with the function random SVD that is in package bigstatsr. And if you use the SVD function in base R, I think it would take like something like 2 hours. So it's really much faster. And we are interested in looking at the PCs in genetics because if you look at the PCs on the genotype matrix, you get what you get is population structure. So PC1 is like a north-south gradient, and PC2 is a west-east. Okay, it's the opposite: north and south, and west and east. So the population structure in Europe. And actually, it's implemented using package rspectra and rcpp. So package rspectra is very useful to get the partial singular value decomposition for a standard R matrix. A standard R matrix or the sparse matrix, if you have a sparse matrix. But so I had to implement this for my my format. And what I did is I did it also in parallel, so it should be even faster than the spectra package because it's parallelized. So what I have also is a function for computing penalized regressions, so penalized linear and logistic regression. So it can be useful, for example, if you want to use the genotype data to predict a disease. So here it was a data set for the celiac disease, which is the intolerance to gluten. And actually using 15,000 individual and 280,000 variables, 6 score, it took only 2 minutes to fit the penalized regression, which is about 10 times faster than using GLMNet. And in the implementation I provide, there is an automatic grid search for the 2 hyperparameters. So you have the hyperparameters lambda that control the amount of regularization. And then if you use elastic net regularization, then you have also the alpha parameter, which is the relative contribution between the N1 and L2 penalties. So if you use the elastic net, you have 2 hyperparameters that you need to choose, so you can test many values. And actually, there is an automatic way to do that in the implementation and choose the best in parallel. So it's convenient and fast. Okay, let's try some function with some data, some smaller data, just to run it quickly here. So let's start with FBM with like 10,000 rows, 1,000 columns. So I started in this test2, so I got a test2.bk file, which is storing the data on this. So you can see that if you look at the object size of X, it's actually a very small data, a very small object in R, so it doesn't take any memory because the data, the actual data of the matrix is stored on disk. And you can see if you look at the file size of this backing file, it's like almost 80 megabytes, which is corresponding to like 8, which is the, double is using 8, the type of data, each element, times the number of rows times the number of columns. Okay, and this save is used to get another file, which is the RDS file, which is actually storing these objects so that you can attach it from so you can reload it from another R session. So you can actually use this data in as many as as many sessions as you want. Okay, so the data, there is nothing inside right now. It's basically only zeros. So let's just put some random values inside. So I could generate some random number corresponding to the full size of the data, but we don't want to do that because it would use too much memory. So what we want to do instead, we can do it by blocks using this split apply combine strategy that I explained before with the big apply function. For this function, you provide the FBM, and then you provide some function that takes the FBM and some vector of indices that correspond to the subset of columns you want to use. So here you want to, for each block, you want to generate some random values corresponding to the size, so the number of rows times the length of this vector of indices. You put that in the columns, corresponding columns. And actually, the big apply function is like an lapply, so it returns something. Each block is returning something. But here you don't want to return something, you just want to fill the values inside the matrix. So here I'm just using null just to return some null, and I combine all these values with C. So instead of getting a list of nulls, I just get one null in the end. So it's just a way to get data, fill the data by blocks. And then if I look at the first 5 values, I get some random values. Okay, now that I have my data, so let's try some functions. So if I want to compute the correlation, so if I access the data as a standard R matrix, use this base function core, or I can use the function bcore and directly on the FBM object, which is basically computing the correlation but by blocks, just to don't use too much memory. Get the exact same results. If I want to compute the SVD, so the partial singular value decomposition for the 10 first components of the scale matrix, so I can do it in base R like this. I scale the matrix and then I compute the SVD with 10 components. And in my package, I have actually 2 functions to do it. One is useful. This one is useful, big underscore SVD, if you have one dimension that is small, and the other one can be very large. But if you have one that is small, you can use this function. And you can see it's much faster. And actually, if you have both dimensions, so that are very large, as we do in human genetics now, you can use this big underscore random SVD and using components, and then it's very fast. And actually, there is a parameter to run this in parallel to make it even faster if you have larger data. So you can basically always use this function if you want to compute a very fast partial singular value decomposition. Also functions for multiple association. So what is multiple association? Is when you want to look at each of your variable in your data, each of them independently, and want to test for some association between one variable and one outcome. So for example, before I had the disease status, if you have a select disease or not. So you have people that have the disease, people that don't. So you have a bunch of zeros and n1. So you can use that as a phenotype. And you want to test each of the genetic variants if they are associated with the disease status. So what you could do is do a for loop over your variables, and then in the for loop you call some LM or GLM to test for the association. But if you have more than 100 variables, then it will be slow because the for loop of calling all the LMs or GLMs will be very slow. And in genetics, we have like hundreds of thousands of variables or even millions of variables. So you don't want to use a for loop of LMs. But instead, I have this very fast function where you can run this, and it's like, I don't know, like 1,000 times faster or something like that than a for loop. From that, what you get is for each of your variable, you get the effect size, you get the standard error of the effect size, and some p-value for the association, the test of the association. So you can plot this. So here it's the histogram of the it's the histogram of the p-values. Also, so we are in R, so we can just use ggplot to plot the results. So what we usually we represent it as a Manhattan plot, which is just for each column you plot the minus log 10 p-value. And here you can see that the causal variables, meaning the variable with the non-zero effect, the true effect on the phenotype, the outcome, are the ones that are the most significant. So as I presented before, you can use some prediction. So here, let's just split in 80% training and 20% remaining as test set. You can use this big SP linear, so sparse linear regression. So you provide the FBM, you provide the outcome just for the training set, and then you provide some indices of the training set that you want to use. So it's useful to have this parameter so that you don't have to split, to subset your data. Your data is on disk, you don't want to make some copies of it on disk or something like that. So it's easier just to provide this, just say that, oh, I want to use these indices to train the model. You can have some additional covariables that are not in the matrix. And actually, what you can do is also penalize differently all the variables, including the covariables that you have here. You can, for example, penalize them at all using a vector of zeros. And then some other parameters, for example, there is this alpha parameter where you can provide a grid of values to test for this alpha parameter. So you get some models, and then you can just predict using the methods predict in the test set and get the prediction. So if you want to learn more about how to predict with this package using penalized regression, you can look at this vignette. So again, I will share the link of this presentation at the end of the presentation. Yeah, so just look at the results, so the prediction versus the true phenotype, the test set. So we get some quite good prediction. Okay, let's look now at the toys case. So we want to compute the sum of each column, but using, I will show like 5 different ways to do it. Okay, so the first one is, you access everything as a standard matrix and the call sum. We've seen that we don't really want to do that. So an easy strategy would be the split apply command strategy using big apply. So for that, you provide the FBM objects, and then this function where you, in each block, basically, you access the block of columns, you take the call sum, and then you combine each of the results with the concatenation, like this. So just doing this, it does it for you, like all the splitting, and then applying the function and then combining the results. And you can do that in parallel as well. It just does it for you. So using RCPP, we've seen this. So you can just make the accessor the data, and then use the accessor as the standard numeric matrix with the number of rows, number of columns, and then the accessor with the parentheses. You just loop over all the columns, then all the rows, and just increment for each column all the values, get the call sums, and return the results. So it's very easy. So actually, what I do in so I have many functions that actually use RCPP in the package to make them very efficient. But in all the functions, I usually provide two parameters. One is for the subsetting the rows, and one for subsetting the columns. So because I don't want to make a subset of the data, I have to copy the data. I just want to use a subset of the data as a subview of the data, basically. And what I did is I implemented this other accessor, which is a subview accessor, basically, where you provide these indices, and then you get a new accessor, but it's an accessor to the subview of the data. So basically, when you look at the number of rows and number of columns, it's basically the length of this row 1 and the length of this column. And when you access IJ, it's accessing the subview of the data. So it's very convenient to do it that way, because you just have to change that plan. And then all the other algorithm, the rest of the algorithm is exactly the same as before. But you can run this on a subset of the data. Okay, so here I run this function with, so this is just giving you the 1 to the number of rows, and then 1 to the number of columns. Then I can do it for the first 10 columns, and I get the same results. And it's there are also functions for that, so it's already implemented in a bigstat that will give you data frame. So for all the columns, you have the sum, so the call sums and the call var. Okay, let's talk a bit about parallelism. So here what I did is I just make a vector that just replicates all the columns 100 times to make as if I had a very large data set with 100,000 variables. So I store the number of cores that I can use. So here 4 on my left. And then I run this function. For example, to get the univariate linear regression, so in the multiple testing, so testing each column individually and testing for the association with the phenotype. So you can see, like, for the number of rows was like 10,000, the number of columns 100,000 here. So it's like very, very fast, 9 seconds for testing 100,000 tests with 10,000 observations, so very fast. So in parallel, it's a bit faster. You could parallelize your own function. So if I had to parallelize this, what I could do is use this big parallelize function, which is working the same as bigapply. So it's splitting your data into, like, not splitting copying, but just the indices of the columns, for example, split in 4. For example, if I have 4 cores, and then the function will be run in each core, like in each of the 4 cores, but for the one of the 1/4 of the data. So by providing this in call equals int, which corresponds to the indices of one block. And then you remember that I got from that a data frame. So if I want to combine all the results together, I can just use bind. Okay, so the data, so it will split in 4 the n cores parts. Run in one R process, it will run each for the 1/4 of the data, this function, and then combine the results with rbind. Okay, it's a bit faster than not using. It's a bit slower than this because it's using processes, so that you need time to start the R processes and so on. But if you use Sparse data set, it will be 2 seconds versus like the time it takes to run the function would be nothing. Okay, so we've seen how to parallelize. Just a conclusion about this package. So using this package, I'm now able to run algorithm on hundreds of gigabytes of data within R and on my computer. So I don't have to use very expensive computers, for example, with lots of memory. So it's nice. So the advantage of using this format with the memory mapping. So first, you can apply the algorithm on data larger than your available memory. It's also very convenient to parallelize your algorithm because the data is on disk, so when it's accessed, it's actually shared. When you have a standard R matrix and run some parallelization on it, it will copy the data to each of your new R processes that run the code. So if you use the 10 cores, you will copy the data 10 times, which is not very efficient. And you would need like lots of memory, so you don't want to do that. So with this data on disk that is accessed via memory mapping, the data is actually shared, so it's very efficient, and you don't have to do anything. So I write very efficient algorithms because also you do less copies and you think more about what you're doing. So for example, you want to access your data column by column and not row by row, as I explained before. And finally, you can use different types of data. So the normal type of data that you typically use in R is the double format, which is a floating point number using 8 bytes. But actually, you can use also like here a float, like 4 bytes instead of 8 bytes if you don't need very large numerical precision. You can use integers, and actually in the data I'm using for storing genotypes, I need only 1 byte. So it's 8 times less than the standard R matrix. So it's also a way to make it more efficient. Okay, I will just quickly present 2 other packages that are similar. So the bigsparser, which also provides an on-disk format, but for sparse matrices. So sparse matrices, when you have lots of zeros, what you can do is store only the non-zero values. So you store the indices and the value corresponding to these indices, but just for the non-zero values. So if you have lots of zero values, it can be very efficient to store it like that. And in R, it's provided by the matrix package, this format called GC matrix, which is the most standard sparse matrix format. You have this the symmetric version of it. And so I provide in this package converters from this format to what I call an SFBM, which stands for a sparse FBM, the file big matrix. I have a few functions available right now, to compute products and cross products between this format and a vector, solve some linear equations. And also I have a compact format when you have non-zero values that are contiguous in columns. That makes it twice as efficient. So I have not a lot of things that are implemented currently in this package because it's just it's quite a new package, a new format. I just implemented the function that I needed for some methods that I've been developing. But yeah, we can add, if you need more feature, we can add more feature to this package. And I developed this package because it's more efficient to use this format that is stored on disk when you access the data in C++ and when you parallelize, because you don't need any copying. So it's much more efficient. Yeah, another package so that I've been developing together with bigstatsr at the beginning of my research work, 6 years ago. So it extends bigstatsr, and you also use bigsparser, and implements functions that are specific to the SNP data, so the single nucleotide polymorphism types of data, which we use in human genetics. In this package, you can have function to convert between formats. So, the format that are used in genetics. So you want to convert them to the FBM so that you can use all these functions. There are wrappers around Plink. So Plink is a software that is widely used in human genetics. So clearly, this has nothing to do with memory mapping. It just, me that doesn't want to leave R when I analyze some data. So I just made some wrappers around this command line software, where you can just run it with a system call and then make the intermediate files with R. So it's just a way to conveniently call this software from R directly, so that I don't have to leave R and do everything in R. I have special function for PTSVD. So I talked about this big_random SVD, which is very fast. So on top of that, when you use genetic data, so in genetic data, you have you have some blocks of variables that are highly correlated. And when you run a PCA on that, what you get is the variance in these blocks of variables that are highly correlated. So you don't care about that, you care only about population structure. So you just you have to prune, you have to remove some of these variables that are too correlated when you do the PCA. So you just some extension of the big random SVD basically. So there are functions to compute polygenic scores. So polygenic scores are just predictors based on the genetic data. So for example, you can, if you have some genotype matrix and some phenotype, you can just run some penalized regression, and then you get some genetic predictor that is called a polygenic score. There are other methods where we actually use summary data a lot in genetics, but I won't go into the details of that. So multiple testing testing the association of each of your variable, each of the genetic variants with some phenotype. I've shown it, and I also implement some other tests. There are also many utility functions and other algorithms that have been developing. And actually, one last thing is that there are many functions that, so basically the same function, but that works not only for FPMs, the format I presented before, but directly on some files. So BIM so that format is a binary file on disk, which can be viewed as a matrix. So basically, what I did is I memory mapped this format, the file on disk, and made an accessor that enables me to access this file as a standard matrix with the accessor the same way as with the FBM. And then when I did that, then I could use all the codes that I already implemented for the FBMs just by changing the accessor to this ping bed accessor. Could just run the other code I already had for the SBM format with a different accessor. So it was very convenient for me to make all these new functions without duplicating the code, just by making a new accessor to this format. Okay, and finally, yeah, so I just want to say, so I'm developing these packages to make it easier for me to analyze this large data, but also to implement and develop new methods, new statistical methods for new methods to analyze the data and publish these methods. So it has been very useful for me to make this package, and it has helped me a lot. So I'm the first user of my packages, basically. But I think it would be useful for many people. So if you analyze only data, you can just use the functions that are already available. But if you want to extend it to, I don't know, so some other mixed data, or develop some new methods for genetic data, or for some other format that is that can be stored as a matrix, then I think it would be useful for you to look at this package and see how we can talk together if you want to extend it and build on top of that. And yeah, usually I have an next sticker, but because we don't meet in person, you won't get one. But if you want to get one and meet someday in person, then if I have some on me, I can please ask, and I will give one to you so that you can put on your laptop. And so the presentation is actually available online. So the slides, PFL, github.io, presentation, and then bigsparser.html. And there is my Twitter and GitHub handle. Thanks for your attention, and I can answer questions now if you have some.
So thank you very much, Florian, for your presentation. So I think someone wants to directly ask the question. So we have already some question on Slido, but Pascal, please go ahead and start asking.
I will open the...
You are...
Okay, thank you so much. That was a good presentation. I really appreciate. I've been following this from Nairobi, Kenya. Thank you. I really won't speak much about the bigsnpr, because I've seen that is relating to human genetics.
Bigsnpr,
I think I've been working more. Sorry?
Bigsnpr.
Okay. Yeah, so I've been working mostly with financial data, and I think I would like to give a shot to the bigstatr package. Anyway, my question is relating to, or just trying to find out, perhaps just to know how long you've taken like to work on the bigstatsr package. That's the first question. And the second one is, I was just finding out how you managed to attain parallelization on the big parallelize function or the big apply function. Because when you opened, because I'm not sure whether I saw a place where you are calling an apply function in R, or is it a case whereby you attained that using multi-threading in C++? So maybe I just want to get that. Otherwise, thanks for that. I've really learned a lot. Thank you.
Yeah. Okay. Let me answer the first question. So I've been developing the bigstatsr and bigsnpr package during my thesis for 3 years. So in it has existed for 6 years now. So you know, it's a lot of work behind these packages. So the second question is how do I parallelize? Actually, I use 2 ways to parallelize. The first way, in some of the functions that I code in C++, when I have for loops in C++, you can just use OpenMP to easily parallelize the for loops in C++. And it's, for example, what I use in this function. And the second way we can parallelize function is directly using R. When you use the standard way to parallelize in R, basically what it does is it just starts new R processes, send the data, run the data in these new R processes, and then collect the results. And it's exactly what this function does. And I can show you with maybe this. So if you have like 4 cores, what it does is it just split in 4 blocks. Run in each block in one process. Will run the function on each of the blocks, and then just collect the results. So it's what how you can parallelize with the apply or parallelize the functions. Is it clear?
So maybe related to that question, there was one on Slido, which was about mostly apparently the R framework used for the parallel. So parallel, for each, to parallel, future, or anything else.
Yes. So I have many use for each because it's very convenient. And at the time, future didn't exist yet. I've been thinking about switching to future, also because you can, I mean, you can do a lot of things with future. There is also this progress R package that works well with future, where you can get some progress bar within the parallels function. So it would be very convenient. I didn't have time to do it yet. So for now, it's for each the implementation of the parallel when I use R and not C++.
So basically, there is 2 levels of parallelization. One is using OpenMP internally in some of the RCPP function, and the other is using different R processes, especially for the big apply family.
Yeah.
Okay.
Yeah.
Is there another live question, or should we go through the Slido questions? If we can go through. So the first question was answered. The second one was, is the FBM, so class object, a save method using compression to save RDS?
No, so the RDS is used only to store the R object, which is very, very small. The R object just store information like the number of rows, the number of columns, where is the backing file corresponding to these objects. You don't store like it was like when we looked at it at the beginning. it was like 680 bytes. So it's a very small data. So there is no compression. There is compression when you use RDS, but it's not useful at all because you don't store anything. You just store you just store enough data to be able to remake the link with the backing file. It's the only thing that you store in this object.
Okay, so it's only metadata basically.
Exactly.
Okay.
The actual data of the matrix is in this backing file. It is stored as a binary file that is not compressed at all. Because I don't think you can use memory mapping on some compressed file.
No. Usually R have to uncompress the data even for to read it. So it will be not really that efficient.
Yeah.
So the next question was from James in the chat. So is there any way to read from MATLAB files, or are we limited to RDS file? So
so again,
related to the question from before, the RDS is actually not the data.
Yeah. So the data is a binary file format on disk. So if you have to read from the MATLAB to this format. So I'm not sure. I don't really use MATLAB, so I'm not sure what is the format. But on the bigstatsr website, I have a tutorial on how to read from large text files. So, like for example, if you have a large CSV file, how you can run from that to a SVM format. But with MATLAB, I don't know this format.
The next question is regarding bigsparser. So will the bigsparse matrix be filled if used in computation? So do we lose the sparse matrix attributes when we do computation using it?
So what type of computation? So transpose x times t times x. So you have to implement it in some way that you so that you don't have to use to do the scaling. Like for example, when you when you do a matrix product with your matrix and a vector, for example, the scaling you can apply it on the vector or the results. You don't have to apply it on the matrix first and then. So I can show you some tutorial on that, or maybe some blog post. Yeah, just quickly. So actually, for example, when you want to do some matrix products, where is it? Yeah. So for example, I don't know if you want to compute x transpose x. So for example, to compute the correlation where x is scaled, if you do a bit of matrix linear algebra, you can look at, you can see that you don't have to do the centering and the scaling. You can do it afterwards. So for example, so the scaling is just multiplying on the left the centering matrix, on the right by some diagonal matrix. And so for example, if you compute x times v, where x is the scale version of this, you can see that actually you can scale the matrix on the right and then center on the left in the end. But you don't have to scale x before and then do the product. You can do the product on some scale version of the second matrix, which is much smaller usually, then do the centering in the end. It's the same when you compute the correlation. With just some, you have usually some linear algebra tricks or some implementation tricks that you can use so that you don't have to explicitly scale your matrix because you don't want to scale your matrix because it's not efficient. You have to make a copy and so on. So it's if you can avoid that, you should.
So in bigsparser, there is no method like to do the solve or transpose transformation of a sparse matrix.
So there is this. Yeah. So there is not an option for the scaling right now. But I'm not sure it makes sense to scale a sparse matrix. Let me think about it. Yeah, I mean, if you need that, maybe you can. If you need this feature, you can open an issue on this.
I think the issue is more general, like if there was any method or anything in bigsparser to do more computation with the sparse matrix and keep the sparse matrix as long as possible in the computation process.
I mean, you have to keep the sparse matrix because it's on this. You can't touch the data.
Yeah, that's why. If you do
so you can't really do any operation to it, like any any modification to the data. It's on this. You can't touch it really. Yeah, so you just access the data. You don't modify the data.
Yeah, so there is some work to do, or be smart about the computation we want to do.
Yeah, you just have to be smart in your algorithm, the algorithm you use, to use some scale version of the matrix, but without actually scaling the matrix.
Okay. And I think there was a question related to sparse, bigsparser as well. Yes. So is bigsparser compatible with all the bigstatsr GLMnet functions?
No, it's for now. No, it's not. Yeah, I didn't think about that. I think in GLMnet they can use the standard sparse matrices. So if your data is not too large because of the sparse format, then you can use GLMnet, I think. But I didn't think about implementing that. The big _sp linreg, for example, with sparse data yet. No, it's not something I did yet.
So maybe more general, to complete that question from our side, any of the function to do a linear or logistic regression within bigstat R are compatible with a big sparse R or not at all?
No, it's not the same thing because when you use sparse data, so when you use the FBMs, the dense matrices, you access IJ, like random access anywhere you want. But with sparse data, you don't really access random elements. You implement the algorithms so that they loop only on the non-zero values. You don't look at all the values and say, oh, is it 0 or is it something else that is stored in the data? It's more like you just loop over only the non-zero elements. It's a different types of implementation, usually the algorithms that work on dense matrices or versus sparse matrices. So they are not really compatible in this way. Yeah. No.
So that answers this question. And the last one. So is your implementation to access elements in big matrices more or less or as efficient as a data table, which use C++ as well?
So usually it's not the thing that you do on data frames or data tables are usually not the same as what you do in on matrices. Yeah, so I'm not sure I understand
the call sums or any computation like this. Is there anything that is more efficient within your implementation?
So I think when you use a matrix, it's always more efficient because the data is stored contiguously. So the access is more efficient because everything is on at the same place in memory. When you use data frames, the columns are stored contiguously, but each column, each of the elements of your data frame is not stored in the same place. So you can just add a bit more time. But usually it's not the same. Yeah, it's not the same function that you use on data frames or matrices, because data frames are supposed to have different types of data, not just numeric data. So yeah. So I'm not sure I guess the question.
So there is another question from Pascal in the chat. So it's saying thanks to you and asking about packages. When are they ready to be accessed? So
The packages?
All already available online?
Yeah, they're on GitHub, on Cran, and they've been there for some time right now. Yeah, you can install them from either GitHub or Cran.
So they're available to use everywhere you want.
Yeah,
yeah. To conclude, so not a question, but a word of appreciation from James to you on the slide.
Yeah, thanks.
Indeed, nice presentation. If there is no other question or comments, I think we are going to conclude this meetup. So thank you all to join and ask questions to Florian. And thank you, Florian, to have accepted the invitation from Erling to present your work and especially the bigstatsr package.
Thanks, Miguel.
Bye, everyone.
Thanks all for attending. Bye.